Hi, thanks for watching this great presentation from Rachel Kaiser at the second annual HVACR Symposium in Claremont, Florida. She did this remote presentation. Rachel is an amazing scientist. Her husband, Eric Kaiser, does a lot of education in the HVAC trade, so she helps to lay the groundwork on the science that we need to know in order to better understand the HVACR trade. Very appreciative to Rachel and all of the speakers and sponsors for the second annual HVACR Symposium. So here we go, Rachel Kaiser and Science, the way I heard it.
I'm going to go ahead and get started, and I want to welcome you to Science the Way I Heard It. I'm Rachel Kaiser, and I'm a practicing scientist. I have been practicing science since I was a very young child, and much longer than any job, schooling, or of a formal education variety or anything like that. So that's why I identify as that practicing scientist. And we're going to talk and explore around science in practice, as well as the theories that go behind it on how we navigate the world around us and how that will then relate to HVACR. So hopefully these, we're going to start here with our first question. What do you think of when you hear the word science? Giving you just a few minutes to think about that, because that's going to be part of today, is its reflection and thinking about what these words mean to you and what your experiences have led you to think about. So do you think of a person wearing a lab coat with a lot of test tubes or beakers in a lab? Or do you think of the person that's diving off the edge of a boat to navigate a coral reef? Do you think of something that is physical, or do you think of something that is living? And so those are some of the topics that come to mind for some people when they hear the word science. And so let's begin by what you think of when you hear that word. So, dictionary definition of science is captured here. You can see we're talking about a systematized knowledge in general. So we're looking at an opportunity in which we're systematically collecting information. It goes back to skills, or reflecting on that application of facts or principles that we gather and then share in a systematic way. And so those will play a key role as we move forward and have our discussion today. A key piece to keep in mind is hearing versus experiencing. And this is as true in science as it is any other field. You have theory of what you talk about should happen, and you have the real world evidence that you collect. Is that real world evidence complete? Or is it aligning or not aligning with the theory that we read about, have demonstrated to us through a variety of methods? That's a very important differentiator. And oftentimes the things that we hear help to guide where we go in the future. And how we learn about different topics affects how we engage and what we want to pursue as we move forward. Like I shared, I have been practicing science since I was a very young child. I got my first microscope when I was in first grade. I played biological exploration throughout my yard all of the time. It was about taking the world that I had around me and putting that into practice and quantifying what I was able to collect. A key piece that I want to cover before we move on is also something called bias. So if you look here, you see this math equation. This makes a lot of people flinch. It's one of those cases that you're often in the camp for or against something like you see on the screen. That would be conscious bias. We also have to blend in that we have both that conscious as well as an unconscious bias. And that's going to be an important thing for all of us to continue to think about for ourselves, because that grouping of biases is going to be critical when we're looking at our outcomes and how we can analyze and move forward from what the data we collect. So before I continue, I want to give a quick short story about one of my experiences and the way I heard it when I was in school. So I was put into a challenge class, and it was 1986. And that was the year that they were putting the first teacher into space. I'm sure many of you remember, it was the Challenger, the whole time of Challenger as far as the actual spacecraft. And I was in a course at my school, and we were going to study rockets. Now, I was very, very excited, and we had our own space. It was separate. We were going to build model rockets. We were going to launch them. We were going to do all kinds of additional study and understanding behind what it took to launch a rocket, what was involved in being an astronaut, what was the pieces that were going to come out from the scientific experiments that the teacher was going to get to participate in. Because from my small town, there was actually one of the teachers from our school district that was one of the finalists. And so it was a really big community activity, as far as everyone was very excited about the upcoming launch and the process in general. So to get to be part of that in the school itself was very exciting. So one of our first classes about the rockets and how they worked was simply, how does the rocket take off? And the teacher stood up in front of us and proceeded to share that rockets launched by pushing off of the earth. Now, I, at the time, was a first grader, and the teachers and what they said about how science in the world worked, that was the place where I was going to absorb, and they were the experts, and I was going to absorb what they were saying. That was the perspective and the bias that I came in with. I, being a very excited kid, after school rushed to my dad to share with him how I had just learned how rockets actually took off. They pushed against the ground. I shared with my father, and he was irate. He was not excited about this sharing of information as I was beaming and glowing about what I had just learned. He was aghast. He proceeded to march over to my elementary school and find the teacher and share his dislike that they had just incorrectly told a whole group of young students that rockets pushed off of the ground to launch. There's a couple flaws in that, and when you step back and think about it. One, how would rockets ever fly when they got to space if their movement was actually reliant on the ground? On top of that, it negates the entire principle of Newton's third law. Now, obviously, as a first grader, Newton's laws were not being outlined in the way that would later learn. But my dad, who was a restaurant owner and cook, very clearly said, it's like, I may only have a high school education, but I know that rockets do not push off the earth to launch. And I wanted to share this because this is a piece that ties into the kinds of things that we're going to be exploring further today. It's often how we hear something initially that plays a big part. And let's see if there we go. So I wanted to step back and do a few takeaways from sharing this story about my first exploration into rockets as a young child. And one of the key and simplest is that rockets do not push off the ground to fly. They leverage propulsion utilizing Newton's third law, and that is that for every action, there is an equal and opposite reaction. So the propellant actually is forced out, and it is therefore of the rocket itself, and it is the reverse force that propels the rocket forward. Another key takeaway is that what you think about a topic is likely going to change and expand and morph as you get new data and more information on it. So it's not a simple statements that tend to be what is important in the end. It's actually about painting a more complete picture about what is happening around us. I also learned one very important piece, and that questions are good, and that even when experts say, or someone that is perceived to be an expert, you don't need to accept everything that they convey at face value. Question those pieces and do it in a respectful way when you're looking at someone that is considered an expert, but that doesn't mean that they have all of the answers. And again, never fall into the trap, the bias, the piece that says that simply because an individual has a specific education level, that they don't know or understand how specific things work. So this jumps us to going to the basis of the scientific method, which is utilized across all the science fields to be able to move understanding and solving problems forward. I'm sure that solving problems is something that almost everyone has encountered in some way. So what we have is we have our first step, which is up here in the red box, is where we list our problem statement or our question that we want to answer. That's the first step that we want to frame out when we are starting down a scientific method process. The next one is here in the orange box, and that is where we get the current state. We start to explore what is the basic understanding of what it is that our question back here is framed around. What are the conditions? What do people generally understand about it? It's the context that will start to help formulate our next step, which is our exploration into what's going to take place. And you start to form what you think is going to happen. That, this yellow box, is often referred to as your hypothesis step. So that's where, like I said, it's iterative. So we take our question, move to our orange box where we look at what our whole circumstances and the understanding that we have, and then we formulate our hypothesis or what we think our outcome will be. Next, we move to what actions are we going to take to test that hypothesis? Here represented in green. And as we go through those actions, we collect data. That data then gets analyzed as we move to our next step, which is here represented in the blue box. That's where we analyze those results. And we start on the process of, do we have enough data to answer the question. This then quickly moves us to the final box in the method, which is draw our conclusion. Drawing our conclusion does not actually end this process, because what we often have happen is exactly as we show here. We come back up. That data and analysis that we have done actually has spawned that, did we ask the right question? Did we have enough information about how the system or the pieces were actually going to work? And did we form the right hypothesis? Any of those steps could have been too broad, or were not framed in a way that actually allowed us to draw a conclusion that we would be able to leverage to go forward. So what you do is you go back up and start over with reframing or re-asking another question, or narrowing what your problem statement is. And then you walk yourself through the method yet again. You again say, what more now do I understand having done this the first time? What can you add to that? How can you refine your hypothesis? What additional actions can you take that would continue to build on testing that hypothesis? Was your analysis itself, was it too broad? Did you utilize too much of a personal bias that led you to see data that was or wasn't actually there? So all of those pieces allow you to continue this flow through the process of asking a question, drawing a hypothesis, testing it, and drawing a conclusion from that specific set and going through again. So you want to make sure whenever you come into these kinds of situations, when you're looking at these methodologies, that you understand what assumptions you're making. You're never when you're in this orange box process for the scientific method, you're never in a state where you're going to have full understanding of the entire environment, or what people are going to know, or what even the system is capable of. So it's important to understand where you're having to make assumptions, because everyone is going to have to make a given level of assumptions. And always, always remember that as you go through, there's no incorrect outcomes. Every piece, element that you go through this method gives you more opportunities to learn about yourself, about the system you're trying to gain greater understanding about, as well as how to become better problem solvers. Now, I know that on a slide where you're just walking through and seeing these blocks, it doesn't have nearly the impact as actually walking through some work around utilizing this method. So we're going to do that now. We're going to practice some of this scientific method. Now, I'm hoping that all of you in some way have available to you some type of a piece of paper. Now, it could be as much as a small instruction booklet, an actual just piece of paper, something that meets that criteria. I'm hoping that you have available somewhere close to you. And then another object with more weight, a pen, a pencil, a Sharpie, some kind of writing implement. Hopefully you have that available, because we're going to leverage these two pieces of items, materials, you can choose whatever word you'd like to use, to practice some of those steps that I just outlined in the scientific method. So we're going to start the scientific method in action. And no, you didn't get rid of the colored boxes. They're still with us. So question, will the paper or the pen hit the ground first? This is the simple question that we're going to leverage to be able to see this process that is called the scientific method in action. So the current state. For those of you here, just write down what you think the current state is. If you don't have an easy way to write, at least think about it in your head. What is the current state? So I'll give you just a few minutes to think about that, and then I'll give a few discussion points. All right, has everyone hopefully had a bit of time to write down or at least think about what they view as the current state? Current state. Let's start here with the piece of paper. I would say it's solid. It has a lot of surface area. I mean, it's white in this case on my example. But given that my question is, will the paper or the pen hit the ground first? And I'm just thinking through current state. My piece of paper doesn't have any holes in it. Those are the kinds of things that I would start understanding. And then as a current state beyond simply the piece of paper, the material I'm going to use, it's also that I work under the overarching idea that we are all going to be affected by gravity because I'm dropping the piece of paper on Earth. And so gravity will play an effect. So that would be my current state. Is I understand that the reason I'm standing here is that gravity is affecting me. So that adds into what our current state is. And then it would be the same kind of a look at the other material I'm going to use. In my case, I have a Sharpie. And again, solid, no holes, less surface area than the paper. And from that, we would then move here to the yellow box, prediction or hypothesis. And that ties right back to the way I heard it. If you hear the word hypothesis, which I tend to use, is that help you think about what it is? Or does simply saying the word prediction, all we need is for you to predict what you think is going to happen when you go back to the question of will the paper or the pen hit the ground first? So write it down, keep it in your head. What's your prediction? So we then move to testing the prediction through actions. So we're going to start the pen. I'm asking all of you to go ahead and stand up. This is the moment to not sit in a chair, not sit in the seat of your van, not sit at your dining room table, but stand up and participate in doing some of these actions that not only test this prediction, but start to make this more of an experience. Even if it is something as simple as a pen and a piece of paper, this is the start of how we get to understand the scientific method and how we can use it in day-to-day experiences. All right, so the first step we want to do is drop the pen. It's a little harder to see and it's going to be less helpful, but if I drop this pen, it fell. I'm going to go out on a limb and hope that your pen also falls. I cannot see if your pens are falling, but hopefully they are. We will then move to the next step where we have the piece of paper. Again, we're going to move to dropping just the piece of paper. All right. Our third and final action step after we've retrieved the pen and piece of paper is we're going to drop them at the same time. Now, we want them to be as close to being dropped from the same height each time. We're not going to time them. This is not about the exact accuracy of a measurement. This is about what we can observe with our eyes, because most scenarios are dependent on our observation and data collection as individuals. It is the addition of instrumentation, gauges, and a lot of the tools that we use in various scenarios that just add to the data that we're able to collect to narrow down the kinds of actions and data analysis that we're able to do. But in many cases, you can do it simply with what you have, which is your eyes, your ears, and your sense of touch. So we're going to bring our items at roughly the same height, and we want to drop them at the same time. What happened? Again, think about that. Write it down if you can, or at least hold it in your mind as to what happened. If you want, you can drop them again if you didn't see. I did not watch my paper and pen on this time. I have to admit, I looked at my slide. So I am going to do it one more time. So paper, pen, drop. All right. That time I actually watched the items fall. So I was able to collect data from the actions that test our prediction. We now move to that next step in the scientific method where we analyze the results. So the first piece goes back to dropping the items individually, not looking at it as a comparison. Did both items fall to the surface below them? This cycles us back to that understanding that we talked about in the orange box of working under the assumption that we have gravity acting on us and the objects around us. Did you notice anything throughout the process of dropping the pen, the paper individually or together that was unexpected? Did your piece of paper waft in a way that you didn't think would take place? Did your pen somersault as it went down? Your options of what you saw are open and limitless. What were your assumptions? We covered one of those assumptions. The idea that gravity was still going to work on all of our objects. That's still an assumption. It's not one that many of us ever get to break free of, but it is still an assumption that gravity is going to work how we have always historically interacted with it. So our final piece for round one of the scientific method is drawing our conclusion. This brings us to that third test step where we drop the two objects together. Which item hit the ground first? Where did you have places for error or bias? For instance, did the two items actually get dropped from the same height? If I drop them like this, is that a cause for error? Is it bias that I'm already anticipating that the pen will fall faster and hit the ground first? So I'm giving the paper a fighting chance? Those are the kinds of things that would allow for bringing in error or bias during our experimentation step that affects what our data is and what kind of conclusion we can draw. Now, I can only speak for my experiment, but in my case, the pen, my Sharpie, hit the ground first. But we need to be ready to iterate and continue to build on this process. And we want to test those assumptions all the time. So our assumption, because I showed it that way, was actually that this piece of paper was flat. I never said it had to be flat. If this piece of paper is now a ball, is it going to fall at the same rate as that flat piece of paper versus our pen? We don't know until we experiment with it again. And that is the part that the scientific method gives us all kinds of opportunities to iterate and repeat so that we can better understand what's going on around us. Our next step, a way to iterate. What if we change not just the physical appearance of the item? What if we change the items? So based on what we just studied in our experiment, we go back to a new question. Which hits the ground first, a feather or a bowling ball? As you can see, I have jumped from the red question. Orange is going to be the orange, the understanding our situation, the world around us, is something that many times people want to skip. What is it that we know about the system that this test is going to take place in? What are those pieces going to be? What do we actually know about the bowling ball and the feather? That's something that you want to have play into what your hypothesis, or like I said, this is your prediction. So again, in this iterative state, what's your hypothesis? What's your prediction between this feather and bowling ball being dropped? When you get to the analyze, what you see is, whether we look at the first part of the video where they dropped the bowling ball versus the feather, just like we did the paper and the pen, or when the second part, when they put the room under vacuum and drop the two. So our conclusion changes because they iterated in that video. So which item hit the ground first depends on which iteration we want to look at. And it comes back to understanding the world that we are looking at and where that data is coming from. Because if I only had shown you the second part of the video and you were not given the details that they had pulled that room down under vacuum, what would your conclusion have been? What would it have been what you had expected? The likelihood is not, because would one of your assumptions have been, well, it would be in a vacuumed room. That starts to help tell us where we need to watch out for places that we can have error in what we have going on around us. If you want to call it error, if you want to call it bias, if you want to call it not understanding what it is that we're working with. And that happens all the time. And that is one of the key learning points, is knowing that we aren't going to understand everything that that environment has. And so it's key to take that and be able to work through, repeat the process, because hopefully we run into scenarios where the answer isn't what we expected. But the other part to just highlight is what the video does is it shows us the difference between what we typically experience in the real world, which is the bowling ball hitting that crate long before the feathers ever came, versus the theory. If you sat in a science class, the theory says that the two should hit at the exact same moment, because it's only because of the air resistance in which the feathers, or in our earlier experiment, the piece of paper, falls more slowly. And that's something that we all need to keep in mind, because the way we hear things, often in a formal science class, is all formulated and tested against theories that don't necessarily have the same experience when you put them in the real world. And that's what we need to realize makes a big difference at being able to leverage the theories in a academic sense versus leveraging them in a meaningful way in the world in which we all work. So this is another important takeaway. In the case, if you had, of our bowling ball and feather, if you had said the bowling ball would hit the ground first, and you only saw that second half of the video where they hit at the same time, you could easily move to the conclusion that you were wrong, and that incorrect hypothesis or incorrect prediction was bad science. And that's not true. Those the incorrect data are great opportunities to learn and are critical for us to actually build not only a better personal ability to solve problems in the future, but actually to grow the entire approach to how we experience the world around us. And so that's why I much appreciate this Ralph Waldo Emerson quote, in which bad times have a scientific value. These are occasions a good learner would not miss. So let's always make sure that we take those bad times and learn from them, because they all have value when you iterate and use the scientific method approach to solving the questions and problems that we face every day. All right, so I've been talking a lot about the scientific method and about how we can know about air resistance, and I've talked about some rockets and all the kinds of things that are probably pretty typically things that you might consider of a science class or a chemist or a physicist or an engineer. But what about why, as HVAC professionals, HVACR professionals, should you care about this scientific method? Does it matter whether you hear something or experience it? As I've been demonstrating with the bowling ball and feather, hearing about a theory of how those will fall versus experiencing them in the real world, not in a vacuum, they have significant differences in what the outcome will be. And here what we're going to do is we're going to take the day in the life of an HVAC technician and see if that really is still a day in the life of a scientist. So let's explore that a bit more. And we're not going to leave our scientific method behind. What we are going to do is we're going to make two changes here. We're going to stop referring to it as simply the scientific method, and we're going to start calling it the problem-solving method, because that helps to not just take what we have heard over and over and transition it to something that I'm sure almost all of us have had of, we have a problem, we need to solve it. That problem then is, what do I have before me? What do I think needs to take place? I then follow through on those actions. I see what is the outcome, and then I decide whether that fixed my problem or if I need to do something more. If that sounds familiar, that is the problem solving, which is the same as the scientific method we've been talking about. We're also going to take this problem solving method and apply that to a question around HVACR. No more rockets. So here's our question. Is HVACR a science? Now, just to be sure we're all on the same playing field, I have a few definitions. HVACR is still heating, ventilation, air conditioning, and refrigeration. And science is still skills, especially reflecting a precise application of facts or principles. All right. So that's where we're going to leverage these definitions related to, is HVACR a science? And now we're going to walk through the different steps of the problem solving method for this question. Are you ready to go? All right, so we've moved to our current state and understanding. HVACR is typically considered a trade. Would you agree? Ironically, the Department of Labor does not even classify HVACR as a skilled trade. Despite that, the list that you see is only the start of the many areas of understanding that so many roles in the HVACR broad field require for executing successfully. Because you don't want to end up being like George over here and looking at a pile of thermostat wire and not having any idea what to do. His problem may stem from not having opposable thumbs, but I think he was also lacking some of these critical abilities of being able to understand electrical or even work the tools. So that's where our current state and understanding from an outside perspective of HVACR a trade, but is not the reality that so many base concepts across such a diverse set of often trades, carpentry, metalworking, building shells, written and verbal communication, all of those pieces play into what you have to do as HVACR professionals. So, our prediction. Now, I have filled out the prediction that HVACR is a science. That is the hypothesis or prediction we're going to walk through, test for and against, analyze, and draw a conclusion from. Because remember, science is nothing but perception. So the Department of Labor may say it's not a skilled trade, but we're going to see if we can show that HVACR is a science. All right, so we have two key areas here in the action portion to test that prediction, to see if HVACR is a science. Now, we're going to start with the survey portion. In this part of the testing, I have already gone and asked a variety of people with diverse backgrounds, with different work experiences, different education levels, different parts of the country, what science by definition is to them. What we will then do, that test, is seeing if those perspectives of a diverse group of people matches with the work that is done in HVACR. So remember, they're defining what science is, and then we're going to analyze to see if those perspectives match the kind of work that gets done in HVACR trades. Our second is we're going to explore one topic. We have limited time and the options are pretty large, but we're going to take one topic and look at that topic that is applicable to the HVACR fields and compare how you usually experience and hear about that topic in a typical science classroom versus utilizing the topic itself as an actual HVACR professional. So let's get started with the action portion. We will start on the survey. And in case, all of them will be marked as to which portion of the action we are covering at the moment. So our first survey is actually comes from What Science Is from a high school math, physics, and chemistry teacher. So they think that science is the study of how to understand the world around us through different lenses of thought for clarity in understanding ourselves and our world. Does that resonate? Is there parts of that that feel that you think have application to the kinds of things that you do as an HVACR professional? All right, our next comes from a commercial HVAC service technician. It's everything. Science is the human endeavor to understand nature. There are rules that must be followed. One must base ideas on data or information that can be tested by others. Ideas are rejected if they fail to support what is known. Our next actually comes from a research scientist. They have scientist in their name. I take that and remember what we want to apply for biases in the different roles. A rigorous approach to gaining understanding that allows us to get as close to the truth as possible at any given time. The product of science is the currency with which progress is purchased. Next, we gather some definition of science from an HVACR trainer. They say, the ever-evolving study of the world around us. Do you feel that that has relevance, again, to the kinds of activities that you do on a daily basis as HVACR techs, professionals, any of those roles in the wide field that is? Next, we have the definition from a sociological mapper. They say the process of understanding and explaining things using observation and experimentation. From a residential HVAC technician, they provided the definition of science as being science is the study of all living things. Our next data point comes from a retired service technician in the electronics industry. And here they say science is a body of knowledge that can be summed up as widely based on animal, vegetable, and mineral, though they aren't mutually exclusive. The overlying condition is that the knowledge that is gained and or known in these areas can be verified by facts and can be measured. Our next data point comes from an HVAC control systems designer. Their definition of science is, it is the way we structure and format data so we can understand and process how things in nature work. It is by measurable and defined means to track and record what we explore during the seeking and testing of our hypothesis. One of our last data points comes from a mechanical engineer, in which science is the methodology for how we learn and discover the world around us through answering questions and solving problems. So this brings us to analyzing these results. And we're parsing this out because we have that two-prong approach. We have the survey data and the topic. So our first piece is the survey. And what is science? I captured a few pieces as takeaways because I do not expect people to have memorized those quotes from a variety of backgrounds as we went through them. Many of them referred to nature, the world around us, as being critical. Do those topics, the world around us, does that not apply to HVACR? A next highlight. Many of them mention study or working to understand. Again, going out, does an HVACR professional also work to understand what's happening with a system, refrigerant, even just as a teacher of the skill set, you're working to understand what it is that your students need. All of these seem to fit under studying and understanding the world around us. And then one of the final points, many of the survey respondents had measurable around facts. So does this also apply to HVACR? Do you not leverage a variety of tools and instruments to collect data and measure how a system is performing? Do you not rely on facts about how something is supposed to work to be able to help guide when you are problem solving or going in and trying to fix an issue that you have arise with a piece of equipment? So this does bring us, do all of these topics tend to apply to HVACR? All right, so we're back to our topic. And just to remind you, we are in our action step around collecting the data that will determine whether HVACR is a science, and we're working on the prediction that HVACR is a science. All right, so you'll notice that one piece, I have gas laws in quotes because they're gas laws. And the term laws often has a very clear definition that pops into people's minds. So that's something to keep in mind, because that falls into the way we hear it versus the way we use it. All right, so we're going to take a little bit of a trip on these topics into a science classroom. Obviously, this is one of my comfort areas, just like that math equation. So it's important to understand that that's part of my bias, is that stating historical facts about the scientists that came up with these laws or theories is part of what gets me excited, is understanding the context and the time and the limitations that they had of what they could experiment with and still draw the kinds of conclusions that we use. So we're going to start here with Boyles Law. This is Robert Boyle, scientist from the 1600s. And he is the one that worked out the relationship between pressure and volume. Now, before we get any further, the key here is these are gas laws. Now, let's take out the laws and let's call that theory, but they still are the gas theories. So we aren't talking about relationships that are going to work if you switch to a liquid or a solid or any of your fluids and the pieces where you start to have multi-phase of a particular compound. This and what we're going to continue to talk about, it's important to remember we're only talking about these theories applying to gases. So Boyle figured out that pressure and volume were related and inversely so. Essentially what we have is shown on a graph and gets even better when we pull out an example. Probably reminds you of something if you went through a lot of regular science class examples, something you'd see in a regular textbook. Look, you have a Bunsen burner. It's heating a given vessel. It has molecules of a substance at a given amount. So in this case, our problem is listing 17.5 milliliters of a particular gas, and it's at 4.5 atmospheres. All of these in units and vessels and things that don't necessarily apply or come up in a real world experience. I don't know about you, but I do not go up and see if the pressure outside is measured in atmospheres typically to see how the day is going to be. Because that's going to be a key thing to keep in mind as we continue to talk about these, because temperature in these theories, it's critical that they be in specific units for the relationships to be comparable. So we walk through, we have this example, and you end up with an equation in which your pressure of your second vessel times the volume that you have in your second vessel is equal to the pressure in your first vessel times the volume in your first vessel. And if in a class setting, you probably get to do a lot of problems leveraging that, in which you plug in numbers that the question above from the textbook provides you into the appropriate spaces, and you solve for the unknown entity. And it tells you with the fixed amount of gas, what's the temperature, because we know the other values. What does that tell us about how to use that in the real world? Are you going to have a static system in which the amount of material doesn't change, and these beautiful Bunsen burners that allow your temperature to always stay exactly the same, and somehow magically, even in this theory, this Bunsen burner keeps the entire space at an even temperature? Does that seem realistic? So this is the example and the kind of problem you'd work in science class, but it doesn't feel that it works very well in the real world. We're going to continue on because Boyle was only the first gas theory. Now we move to Charles. So we've jumped from the 1600s up to the late 1700s. And here we have Charles' law, where he figured out that there was actually a correlation between temperature and volume. So here, when you get your temperature increasing, your volume increases and gets represented by a graph. It's this nice vertical line, which, by the way, if I goes up. So, and a key part to remember is, once again, we are showing that our temperature is in Kelvin, not your Fahrenheit that you often have. It's not even the Celsius that many scientists, or Europe or Canada actually, all leverage either. It's a switch that you have to actually change the temperature to do these science class math calculations with. The key takeaway becomes volume is directly proportional to temperature. Again, though, it works the same way. You end up with a textbook style question setting up the scenario that Charles had tested with magically other components, amount, and in this case, when you have temperature and volume, so pressure as well as amount are being held constant. Are those real world applicable? All right, our third one, we move up to the 1800s. Here we have Gay-Lussac and his experiments, where he built on the work that Charles had been doing and figured out that there was actually a correlation between pressure and temperature. But again, it's as long as we hold all else constant. So volume doesn't change and amount doesn't change. And we still have a direct proportional relationship of one goes up, the other goes up. Here we have another example where we get a beautiful equation. You do a lot of plug and play when there's solve for a given piece and figure out what the pressure is. Wonderful. And again, the handy dandy Kelvin, taking the relevance of this law, or honestly theory, and applying it. And every one of these, the piece that's critical to remember is it has to be the gas in a, so in this case, aerosol can. It doesn't work when we don't have only a gas, these math equations. So is that the relevant way to bring it for an experience standpoint? We don't stop there, though. We then move to taking Boyle, Charles, and Gay-Lussac's laws, theories, and combining them together to do the combined gas law. This, in one equation, we get the relationship between the temperature, the pressure, and the volume. But again, the amount is held constant. How many real-world scenarios do we have in which the amount is never changed? It's a closed system in which your amount cannot change. There are examples, but they are not large in number, outside of controlled where you're intentionally setting them up that way. You get to do some more math with another equation that now has the temperature, the volume, and the pressure. And everyone still likes in science class to refer to it as the law. But that law is so narrow in its scope. You're still in an ideal. It also is an ideal gas that is being leveraged to be able to calculate these problems out. In true form, we just keep building. We add on Avogadro. Avogadro was working separately from the gas laws, in which he expanded around the relationship that you have when you have when you're looking at a gas and the volume. And this piece, his approach makes two key assumptions, where you have temperature and pressure constant. And this is the first time that we actually bring an amount into being variable. So here, where you have 2, and in this case, mole is the amount. It is the amount of the molecules. And you add it to how much the amount, in this case, of oxygen, you then only get 2 moles of water, because the moles isn't how many atoms, it's how many molecules. Sure, this is exciting, because now this is the key part when you're looking at amounts, is that number of moles is this fun Greek letter that looks kind of like a long-legged N. Because that mole is the amount of any substance. And it's based on 12 grams of carbon-12. Not carbon-13, not carbon-14. You have to compare it against carbon-12. Now, I'm not sure about you in your typical interactions, but do you ever go and analyze how much you have of something versus carbon-12? Even I don't do that in my lab. 1 mole of that substance then garners a particular constant, and that is known as Avogadro's number. So when we're looking at this from this perspective of from a science class, you end up doing a lot of these examples leveraging Avogadro's number, 6.02 times 10 to the 23rd. And then it's always the, did my teacher allow me to have that on the test before we took it, or was it something that you had to memorize? Does any of those questions apply when we're looking at real world experiences? You continue, you bring Avogadro's number, you bring in how many moles and the volume, and you again get your equation, you look at these situations where you've set up for this ideal gas, and you play the math game. And you figure out that, oh, that relationship means that they're directly or indirectly related. That's what it's telling you. So now that we have addressed the relationship between temperature, pressure, volume, and number of moles, we get to jump to the ideal gas law or theory. Let's call it the ideal gas theory. Now, the best part of this is ideal in its own utilization is just that. It's the theoretical gas. So you have the theoretical gas theory. Does that sound particularly useful of an equation? I'm going to have a theoretical gas theory. It does bring a lot of questions. So here what we've done is we've combined Boyles, Charles, Gay-Lussac's, and Avogadro's approach and relationships about ideal gases and put them in one place. Some key pieces. We still have the issue that temperature always has to be put into Kelvin because this crazy R, the gas constant, requires the use of temperature in Kelvin. This works, this theoretical gas theory still has 2 key assumptions, and that is that the atomic volume itself is ignored and that you have no intermolecular forces. Those are critical and why it is really the theoretical gas theory. So As we continue to build and we walk through the science class and we're doing all the gas laws, we then come to Dalton's law, or often referred to as the law of partial pressures. This is where you take one gas that has a given pressure. It is actually additive to the second gas that's in that system for a total gas pressure combined from those two. So your equation, depending on how many states you have, is your total pressure is dependent on every pressure of what's in that system from a gas standpoint. The key piece here is you then get to do a numerous iterations. And then there's this point of, we already know that this theory of partial pressures breaks down at high pressures and low temperatures. Because when you hit those areas, it takes gases further and further away from being ideal or theoretically relevant. So then our class, our science class here, is moving us to real gas laws. This is sounding better because I've brought up over and over what we have is we have these ideal scenarios and these theoretical gases acting in a relationship. So it's the late 1800s now, and we have van der Waal. And he worked out a way to explain why gases were not matching up with all those previous scientists' work that said this is how gases should behave. So van der Waal came up with an equation, because that's what you do when you're iterating in this case. They had these equations from Charles and Boyle and Gay-Lussac and Avogadro, and you put it together, and then you run into the problem with Dalton's partial pressures and it breaking down at those high pressure scenarios or low temperature scenarios. And how do you explain that? So van der Waal added a correction factor. So now that PV equals nRT equation now has some correction factors. So correct for the attractive forces that we are happening between the molecules, and correct for the volume of the particles themselves, giving you the ideal pressure times the ideal volume is the nRT. That's what we're used to. That simple combined relationship now just got a lot more complex. Because do you have an instrument that figures out the attractive forces between molecules? How about the volume of particles? That is not an area that many people can just pull out of a bag and measure. So this is where our science world meets the real world. Our ideal theories, what we've been looking at with all of these advancements through the 16, 17, and 1800s, was based on the same concept as looking at Earth as flat. To be able to work out how the gases related, the pressure, the temperature, all these things, they needed to make a set of assumptions so that they were able to have a data set that allowed them to draw a meaningful conclusion. But they had to make a lot of assumptions. This is what led us to ideal or theoretical gases, because there's almost nothing in the real world that fits into that ideal. You then move that the Earth is not flat. Sorry if I just burst someone's bubble. It is spherical, and this is our real gases. They are complex, they have dimension, and they don't behave as if they're flat. This is where those theoretical gases and the math and the pieces that we've just been walking through break down. But those gas laws, those gas theories have real world correlation, but it's not about taking those pretty textbook pictures and doing some math and saying what the volume is going to be. That's not going to be applicable or value added to anyone, a scientist that works in a field or a scientist that works in a lab. Outside of that classroom setting, those ideal gas laws are about their relationship and not about the graph, the math, or the pictures on unrealistic expectations of assumptions. So we're going to come back. We're back at Boyles Law. So we're back in the 1600s, and the fact that pressure and volume are inversely related. Now, a piece here, when we start coming to real world, volume in these cases is often helpful to think about. It's the space between the molecules. It is not in the same sense of volume that we would think of a vessel. Think of this volume that Boyle is referring to as the space between the molecules. So if we move to the idea of a nitrogen tank, and you're in the process that you're wanting to fill a line set and coil and with your nitrogen tank, you have a pressure reading on that tank. You use the nitrogen and you start filling your line set and coil. Your pressure on that gauge goes down. Now we're going to only look at the gas, the nitrogen in the tank. That nitrogen in the tank, as the tank volume is going down, the space between those nitrogen molecules inside the tank gets larger. So your pressure that you're seeing on the gauge goes down, but your volume of the gas, which is in this case the space between the molecules, is inverse. It actually increases. So your space between your nitrogen molecules in that nitrogen tank gets larger because your vessel, the tank itself, did not change size, but the nitrogen gas left in the vessel did not just hang out in a little corner like an introvert. It filled up the nitrogen tank, therefore increasing the space between the nitrogen molecules. And so it's those kinds that this relationship is applicable and helpful to know without ever needing to do any math. It's just as your pressure goes down, your space between your molecules goes up. The same is with Charles' law. Here, remember, Charles, 1700s, volume is directly related to temperature. In the real world, do we care if temperature's in Kelvin? No, because it's about the relationship that if you increase volume, you increase temperature, or if you decrease volume, you decrease temperature. And again, we want to think of this volume as space between the gas molecules, because in these scenarios, we have to also remember we are still only talking about gases. So if you look at your airflow testing of a furnace supply and return, when you have your temperature increase, your space between the molecules, because they have now heated up, they are acting with a lot greater energy and movement, and that moves the molecules themselves further apart, increasing the distance between them, or sometimes referred to as the volume of the molecules. It continues because obviously temperature, we know from the late 1700s is related to pressure. So here, if you have a refrigerant tank that you filled at 70 degrees Fahrenheit, because is that not typically a temperature unit that in the real world in the United States we use? Yes. Do you need to convert that 70 degrees Fahrenheit to Celsius or Kelvin? No, because this is about the relationship. So you fill the refrigerant tank and the gas in it it's in a gas form predominantly. We're going to only be considering that, is placed in a truck, and that truck gets to 130 degrees Fahrenheit. What happens to the pressure in the tank? This is where the gas theories are going to be very helpful for you. The pressure goes up because we know from the 1700s that they are directly related. Temperature goes up, pressure goes up. We have 70 to 130, so the pressure in that tank is going up. So you have to take that into consideration when that refrigerant tank gets filled. That comes down to the safety, the DOT regulations, everything you have about putting items in a truck boils back, not sarcastically, to the gas theories and why those pieces are in place. So it's about the relationship. If we take here and we combine all these pieces and you look at the combined gas law approach, where you have temperature and pressure and volume able to change, a TXV or a thermal expansion valve is a perfect example. Now, this is real world, so we don't have only gas. We know that liquid can come through. So you still have a case in which your temperature, pressure, and volume, as it works through your valve, follows all the relationships that we would expect through the combined gas theory, even in the real world. And those are the pieces that we can then leverage to make them applicable for a real world experience. We take all of those and we come back to ideal gas and filling a refrigerant recovery tank. It's the same piece as we've just walked through for the truck example. You're filling that recovery tank. These relationships matter. It says ideal in the theory. This is the theoretical gas. But when you take that out and you only think about gas theory and think of them as relationships, applying those to filling a refrigerant recovery tank helps you be safer and understand where the rules and regulations around weighing and understanding the pressure changes and what can happen on storage and these things start to fall into place. We move to Dalton and his law of the partial pressures, where we need to remember that all pressures are additive. So if you have a contaminated system and you fall under a poor evacuation practice and you have a value that you think that you have hit as far as a pressure for your system, that pressure is not simply related to the refrigerant that you were trying to evacuate. It also had the component from the contamination. So that value that you're getting, no matter how accurate or good the devices that you're collecting that pressure on, the contamination is giving you false amount because the pressures are additive. And that's a way that you can see that, again, this theory around an ideal gas that is not actually available in our real world can still help you understand and think through some of the pitfalls that you can hit as to, is this a system that likely has contamination? And what does that mean then to my pressure value that I have actually coming through on my measuring devices, whatever ones you use. Last piece here, real gas behavior. This is what helped to spark a lot of the work when you added in the information and the correction factors on the theoretical side, because this is where you can see right here, the red line is representing what an ideal gas, if we just did those math and all those science classroom examples I gave, this is how it would map out. You put a real gas, which is what we all have to interact with, be it in an actual lab setting or out in a field, as in not a farm field, as in the field. Your real gas doesn't behave like your ideal gas. So we have yet another compounding piece that further provides evidence that it's about the relationships that start to tell what is meaningful from these theories versus what isn't. And here you have real gases having lower pressure than ideal gases because of the intermolecular forces, and real gases having larger volume than ideal gases because the molecules have volume. And this is what van der Waal tried to come up with correction factors to address. But does that math matter in an experience? That relationship that the different gas theories put forth is the critical part for understanding refrigerant systems. It's not simply looking at applying the gas laws as written, because our refrigerant systems that you deal with are not simply gas. But it's the principles behind them that there are a lot of principles behind not just the gas laws, but other pieces that are topics that would take almost as long or longer to talk about on their own, such as phase diagrams that start to come into play when you're looking at these refrigerant systems. The refrigerant is often a gas and a liquid. Does that mean that all the relationship that we learn from the gas laws goes out the window? The answer is no. But does it apply in the same way because you have multiple phases present? That's where you get the additional principles needing to be applied. And it's important to remember that the math and the calculations that you walk through time and time again in science classroom styled settings aren't the important part. Those are there to help demonstrate the relationship. But if you take that and switch it to applying the real world scenarios like we did that are relevant to the kinds of work that you do, you can see those relationships at work. So this brings us to the analyzing the results as we go back through the problem solving method. So we have the gas laws or gas theories. Switching the perspective from what we often hear in a science classroom of, look at this equation, look at this graph, and what does that mean for this ideal gas? But we switched that perspective. We adopted it to, this is the real world. We have mixed systems in which the gases are not ideal and they are not purely gases. But that change in perspective and not being concerned on what the math tells us, but only on the relationship, makes it easier to apply that relationship information to what an HVACR professional is going to need. So we now move to our drawing the conclusion. HVACR employs a systematic approach to solving problems in the real world. You're measuring, you're experimenting. All of those are part of troubleshooting. Is that not correct? Many topics. Today, I only was touching on the gas laws or the gas theories, but the options are endless of where you take these traditional science class topics and you just do a small refocus, and the practical utilization of those theories remains crucial to being safe and effective at applying them. So my conclusion is, based on the data we collected through the survey and the topic analysis, is that HVACR is a science. So what does that outcome mean? We need to look at options that focus on application of these scientific principles, not classroom outputs. Being able to answer the questions on a typical style exam is not helpful for being able to use the ideas in a way that meaningfully drives forward in many, many applications. In all of my career of working in a laboratory, I have never needed to apply Charles, Boyles, any of the ideal gas laws in a mathematical scenario. But understanding the relationship actually correlates very well to the same kinds of experiences that an HVAC service technician would have of having gas and a mixed system in a piece of equipment I have when I have an instrument that leverages gas. It's about the relationship and not about the equation and ideal and what those pieces are that formulated being able to do that kind of graph between them. The key here is we don't want to think about this as an either or path. This isn't wrench turning versus the foundational concepts. Neither case is very good on its own, even if they end up going towards the same place. It is not two separate paths, and this is not a flat real world. The way we hear and then experience these different topics makes a huge difference on how we can leverage them going forward. I hope that I've been successful at demonstrating some of the key pieces around reframing an important topic and how that actually makes it real world relevant for the kinds of work that you do every day. What we want to do is take the two paths of scientific principles and in-field actions and combine them to have the most successful outcome possible. I get very excited about science. I like to learn it, I like to experience it, and I like to practice it. Are you someone that is now getting excited to find out you work in that science field as well? It's not just about the kinds of things that many people go to when someone says science, of test tubes and radiation, molecules and DNA, microscopes and rockets or coronavirus. Those are only the starting point for some of the academic classic fields of science. The difference is that the definition is not that narrow. The going through the problem-solving method, looking at the question of, is HVACR a science? The data that we analyze today says the conclusion is yes. What we always need to know is you need to iterate. You need to think about it, question, what are your biases? So when you're working the next time, do you think you'll ever feel like you're a scientist? Because remember, being a scientist is not about how we look, whether you're a dog or a person. Just because he's wearing a lab coat and goggles does not make George an actual scientist. It makes him visually look like what many people think of as a scientist. What you do as HVACR professionals is far greater a science than anything George was ever able to do. It's about your approach to the world around you, because we can all be scientists. I want to thank you very much for your time and attention today. I hope that you enjoyed the presentation and that you're able to be safe with everything going through. Questions, comments, or thoughts, I am open for the rest of our time that we have, either through the chat or verbal questions are available. And if you think of anything else, I am available at HVAC Chemist. Question is, a closed system of a fixed volume where the mass doesn't change, every refrigerant system. Yes, I mean, they're closed on on one level. They are, the theory is a fixed volume, but when it comes to troubleshooting and things like that, that's when that assumption that it is a fully closed system comes into question. And so that's one of the things that you want to keep in mind in that scenario. And it's where things like understanding the relationships and looking at the phase diagrams. And then, of course, the chemistry piece comes into place, because as soon as you actually don't have a closed system or you don't fully do evacuation, the chemistry fun starts from a scientific what's going on standpoint, but not as a technician trying to have that system operate as intended. And so those are, again, some of the things as far as iterating and moving to the next thing of this piece of information of my assumption is it's closed. Is that a correct assumption comes into play, and how you can build on that, because that's when it's operating as intended. And how many times is that the case when something's broken? And yes, mass and mass flow are different, very critical pieces. And if you look at those, that would be its own topic on taking what you tend to learn in a classroom style setting and actually looking at the application components, the topics over and over, countless of the other talks that are taking place across the symposium fall into this category of distilling it down into the relevance versus spouting what you would have in some kind of a scientific textbook, and making that applicable to the types of things that are going to give you the information that you can apply and make meaningful problem solving progress on. The question that just came in is, do I work with the development of refrigerants? And I do not actually work with the development of refrigerants specifically. I understand them well. My classical training is as an inorganic materials chemist. So I've actually done a lot of work on studying and developing diffusion barriers for semiconductor chips, as well as work on the different kinds of films and things that you would have to have for stainless steel protection and things like that. As far as when it comes to the refrigerants themselves, then you're moving typically to an organic style in which you're looking at mixed systems and how they interact. It works in a basic chemistry standpoint, but I do not work with the development of refrigerants specifically. I do tend to be very good at being able to say if you have what the refrigerant compound is and a particular contaminant, then as a chemist by training, I am able to say what is likely a slew of the particular compounds that you could have coming out to have some safety mechanisms put in, as far as like, this is the kind of really scary acid you could be having formed and things like that. But I do not actually develop refrigerants. I develop other kinds of molecules right now. Thank you all for attending the class. I hope that you enjoy the rest of your symposium experience.
Thanks for watching our video. If you enjoyed it and got something out of it, if you wouldn't mind hitting the thumbs up button to like the video, subscribe to the channel, and click the notifications bell to be notified when new videos come out. HVAC School is far more than a YouTube channel. You can find out more by going to hvacrschool.com, which is our website and hub for all of our content, including tech tips, videos, podcasts, and so much more. You can also subscribe to the podcast on any podcast app of your choosing. You can also join our Facebook group if you want to weigh in on the conversation yourself. Thanks again for watching.